Okay, so we can measure force versus length of the rubber band. We've done that by hanging weights in the rubber band, measuring its length and how much weight it's supporting. We get a force versus length graph that might look something like this. And that might, you probably have a characteristic like this where it relaxes a little bit, then it gets stiff when it gets out toward its breaking point, okay? So it usually has that sort of characteristic. It's not perfectly linear, but it stays pretty close to linear, okay? I'll say it's not linear, but it's not far from it. Not too far, I won't put two in there. So you can approximate it with a straight line. And you can say, okay, here's length L sub 0. And the force equals, let's just say that the force out here is 4 newtons and the length is 12 centimeters. So there's a point on the graph. We found that point on the graph, okay. Say 12 centimeters, okay? And length L sub 0 is 5 centimeters. And then what's the equation for your force? It's back to algebra 1. Okay. Well, the slope of this graph is 4 newtons over 7 centimeters. Okay. Linear model, there's your slope. Okay. If you have a point on this graph, then since you got L naught equal 5 centimeters here, the slope from here to here has to be about 0.57 newtons per centimeter. So that that's your point LL. We know that flow from here to here, your run is L minus 5 centimeters. Your rise is F. Let me write that out correctly. Okay. F over L minus 5 centimeters equals F. And 5 times 0.57 is like 0.29. 2.9. Newtons. That's the most direct way of reasoning this out if you know what L naught is. You just set the slope equal to the slope. Slope is rise over run from this point to this point. The run is L minus L naught, which is L minus 5 centimeters and so forth. So anyhow, we get this force. Okay. So question is now, how much work to extend to length? I want to use X, but I don't want to use X. I want to go ahead and use L. Given length L. So how are you going to determine that? Well, I'm going to do this on the graph. If I pick a tiny length increment here, then the force is somewhere between this and this. Does that picture make sense? Can you see the little blue dotted lines? Because they can be a little faint from back there. I can make them darker. Okay, so I've got a little delta L here. Your average force is somewhere in this interval between here and here. Okay. Not much leeway for that average force. Okay, well, what's the length look like here? I mean, just to put some numbers on it, if you want to think in terms of numbers, it's 7 centimeters from here to here. So I'd say it's probably around somewhere in the neighborhood of 8 centimeters. And your force looks like it'd be somewhere in the vicinity of 2.8 newtons. Now, if you plug in 8 for L, you get 0.45 minus 2.9, 4.5 minus 2.9. It's more like, I said like 2.8, I meant 1.8. It's a little less than halfway up here. Okay. And if you got 4.5 minus 2.9, give you 1.6. Okay. So you could estimate numbers, and you could even say, okay, now if my delta L here, how many centimeters is that? Well, if that's 7 centimeters, then this would be 3.5, and 1 centimeter would be about there. It's maybe half a centimeter. If that's half a centimeter, and your average force is 1.6 newtons, then you can figure out how much work is associated with stretching it through this length increment, right? Okay. So you do that numerically. You could even use the function. You could say if the length increment goes from 3 to 3.5 centimeters, you could figure out the force at 3 centimeters, the force at 3.5 centimeters. And then it's not, it's like, I'm sorry, from 8 to 8 or 7 to 7.5. You can plug in the lengths and you get a range of forces, and you kind of take the average in that range and multiply it, and you get a reasonable estimate of how much work is done. And since this is a dang rubber band, that's probably good enough. You don't need to go to the point of pulling out the calculus and integrating. We're going to do that anyhow. We want to understand what the integral is telling us, also how the integral is set up. So you don't want to spend too much time on this. but there we have it. So I'm going to say the typical delta L interval we're going to say with sample point L star. Does this strike a chord with what you learned in calculus? Did you use this sort of development to drive intervals? Well, maybe, maybe not. Your typical delta L increment with sample point L star. Now, all I'm saying is like, okay, this is between 8 and 8.5 centimeters, okay? Pick any number between 8 and 8.5 centimeters and calculate the force. Doesn't make much difference. If you pick 8 centimeters, pick 8.5 centimeters, you're going to have a little bit of difference between those two. If you want to be more accurate, you can average them. But right now, we're just going to say any old sample point works. Then the force is approximately I'm going to use F star delta L, F star representing the force when the length is L star. So by that then I mean if your F star delta L is this times delta L. So that's how we can approximate the force on any interval. Now, between here and here, we divide this thing up into a bunch of intervals. And, you know, my logic skipped a step. The force is approximately this, not the delta L on it. The work is your force times your displacement times delta L. Now, I'm going to use a notation that I hope is familiar to you from calculus. There's just delta L here. I'm going to call this delta L sub I, like the ith interval and their n open. Does that make sense? Have you seen that? Okay. So typical delta L sub I, the sample point L star, L sub I star, you get force F sub I star, which is based on your length L sub I star, and you get work is this. So you subscript your work. So now we're talking about the work on a typical interval, on the ith interval of n subintervals. So the work from 2.9 centimeters to whatever length L is sum of these work contributions. And the sum, that's the sum of these things. Okay, so work sum of your W sub I out to whatever length you want. In this case, maybe it's out to length 12 centimeters, okay? But maybe you want it out to here, maybe you want it out to here. Okay, so sum of your W sub I which is sum of your sum of this, same expression, which approaches the integral from 2.9 centimeters to L of now we've got a problem. I'm talking about the work from here to length L, but L is going to be my variable of integration. So I'm going to back up and say the work from 2.9 centimeters instead of length L, I'm going to use a fancy script L. Okay. So what we're doing is we're dividing this thing up. Here is length script L. So place my printed L here with a script L. And now my limit on the integral is not going to be the same as the integral of integration. Alternative would be to change my integral of integration to some dummy variable. Easier to change that one. And this, by the fundamental theorem of calculus and the derivation of fundamental theorem of calculus, which I hope you have some inkling of, approaches. Okay, this sum approaches this interval. And you get, you squeeze the sum between upper and lower sums and all that stuff. You see some of that in calculus? Yeah. Okay. So, all that machinery, but it really comes down to just this sum becomes this interval, and now we can integrate it. Okay, now to integrate this, I don't want to carry all those numbers and units around. Okay. So too cumbersome. Just comes down to this. Some multiple of L minus some number with respect to L. And this number I'm going to call K. It corresponds to the spring constant and the problems that you might or might not have done for homework. Okay. And this is your L naught, same as what we had here. So I can replace K with this expression with units. I can replace L naught with 5 centimeters if that's what it is. Okay. But this will apply generally to any rubber band that we can approximate with a straight line graph. Any rubber band for which we can approximate force versus length with a straight line graph. So, a real easy interval. Do that interval. Did anybody ever hear it stop?
I thought it was recorded.
That's why we're so quiet.
It tricked everybody.
Here I've got a rubber band. It sort of matches the rubber band in the model that we're using. Maybe. We haven't measured it, but let's just assume it's about right. If I let this 170 gram mass stretch the rubber band out, length of the rubber band goes from 10 centimeters to 20 centimeters. Okay. Now, if this is an ideal elastic object where we have a constant, well, we have a force constant. Okay, that would correspond to the slope of that graph that I used to approximate the actual rubber band data. Okay. If that was accurate, as it would be with an ideal spring, there's no such thing as an ideal spring either, but if it was so, then what would the force constant be? Because what we had was I'm going to pretend this rubber band was a string and hanging from some solid object, not my fingers. Okay. And down here I had 170 grams, which means force of gravity is 1.7 newtons, actually 2% less than that. Okay. So it'd be 167.46, 1.66.6. Okay, if you want to use 9.8, maybe I could be all. Anyhow, there's a force of gravity. Now, here it is, supported with no stretch. Now down here, hanging further, I can put bottom lines there, and the distance from here to here is 10 centimeters. Not a very well thought out picture, but that's common. Okay. So what's a force constant? I'll use X even though it's vertical. I could use Y, it doesn't matter. But you're usually going to see X. Okay. Force equals, very obviously, (1.7 newtons over 10 centimeters times X, if it's linear. That doesn't make sense to you, ponder it until it does. Okay. You really need to understand that. I remember being confused on that. I just saw a formula and then what do you do with that formula? And, you know, so I was kind of swimming around in the ozone for a day or two till I realized, oh, duh. Get to the oh, duh on that thing so it doesn't cause you to stumble. Okay. Now, the other thing is the force exerted by the rubber band is opposite to the direction of the 10 centimeters, so it's actually negative. that subscript I'm putting in the force is elastic. Okay. And X is your position with respect to equilibrium. If you've been reading anything, you know that. Okay. Not any problems. That's been pretty well emphasized in the most recent assignment was due. Okay. Now, when I say position at equilibrium, I don't mean the position at equilibrium of the mass on the string. I don't mean that X equals 0 is the equilibrium position of the mass on the rubber band. In this case, the equilibrium position, when the mass is being suspended, this thing's going to break if I'm not careful. Okay, there's equilibrium. Okay, now there's equilibrium for the rubber band itself. In measuring from here to here, I was able to determine K. Now that I've determined K, I have a system where this is now the equilibrium position because we see it's not accelerating. Now, if I pull it down, it's going to come back up, right? Or if I pull it up a little bit, it'll go back down. If it's a good spring, if it's an ideal spring, and there's no air resistance or anything, it'll keep bouncing up and down forever. If you have a really good spring, it'll keep going for a while. But a spring is still going to flex, create heat, thereby lose energy. Okay, so in the real world, we don't have ideal springs that we can use in lab. Got some pretty good ones. We don't have any ideal. Okay, so anyhow, X is position with respect to equilibrium of the system. Okay. That might be a little bit confusing. As I said, X is 0 here. It's 10 centimeters here. So let me just say what we've got now. Now that we want to measure this thing bouncing on the end of the spring, this is our new equilibrium position, and our new equilibrium position, X is 0, okay? So this is our equilibrium position for measuring the force constant. This is our equilibrium position for measuring the bouncing, oscillating mass. So if we now pull this thing down here, let's say to X equals 6 centimeters, how much work did we have to do? How much energy do we have down here relative to what we have here? And if we know how much energy we have here relative to here, we can figure out what its kinetic energy should be when it's back here. Okay. And again, that's part of the assignment. I can't take the time to do a lot of examples, and that should click for you if it didn't click in the process of doing the assignment. I'll just say that at this point, we say we have stored energy from 0 to 6 centimeters, kx dx is this. Your K is 0.17 newtons per centimeter. K is not negative. The elastic force is negative. And I'm kind of glossing over the whole question of signs here just for purposes of time. Well, we measure that 6 centimeters squared is 36 centimeters squared. Take half of that is 18 centimeters squared. Okay, and 17 times 18 is 306. 289. And 18. 5. Okay, well. Approximately 3 Newton centimeters. Okay. Within 0.03 Newton meters or 0.03 joules. And again, those units need to be very familiar too. Okay. If the thing is now released and the rubber band does equal and opposite work on it coming back here, how fast will it be going here? Well, kinetic energy is going to be 0.03 joules. If you get all the energy back, because 0.03 joules is the integral of the force being exerted from here to here. Or if you wish, the average force times the displacement. Okay. So there we have it. The 1/2 mv squared is going to be 0.03 joules. Mass is 0.17 kilograms, half of that's 0.085 kilograms. 0.085 goes into 0.03, okay? About 0.4 times, 0.3 or 0.4 times. Okay, that's at 0.37 times or something like that. So the V squared would be 0.37 meters per second, meters squared per second squared. Square root of that would be about 60 centimeters per second, meaning when you release it, it gets up to velocity of about 60 centimeters per second. If I did that in my head, halfway correctly. A lot of places I could have messed up calculations, but I think that's probably not too far off. Well, that's a fundamental kind of problem. Just very fundamental, okay? So you want to make sure you can solve that problem. Now the work energy theorem, which nobody could clearly state a few minutes ago, to start, it's everything. What I talked about last time developed from the idea of you accelerate an object with some net force through some distance or for some whatever, okay? And you find out that independent of initial velocity, the change in kinetic energy is always equal to the force times the displacement. Okay. net force times displacement, or the integral of net force times displacement. The integral from x equals a to x equals b is the work done on that interval by the net force. Call that the work net. And of course, that's a change in kinetic energy. Now, we danced around the idea of potential energy. I talked about it some last time because the book does kind of talk about it out of turn a little bit in chapter 6. Chapter 7 is all about potential energy. The work energy theorem is your guiding principle. It's not, well, when I do this problem, I do this. When I do that problem, I do that. And there are 10,000 different examples, and you can't remember 10,000 different situations. You go back to one principle and work it out from the principle and get in the habit of working it that way, so that then you can solve the problems you're going to need to be able to solve. Of course, you've got to solve a lot of problems within physics. That's all there is to it. Okay, so your book is starting to use a different word, and unfortunately, I don't remember what the word is. It's a good word. Okay. I'm going to explain it like this. It's like in the rubber band, you have a conservative force. And remember what a conservative force is? How many remember the definition of conservative force? Talked about it a lot last time. It's path independent. Is that what you're going to say? I'm recording, so you can't say. It's path independent. Example I gave, lift a concrete block, drop it. Oh, I didn't even have a concrete block in that arm. Shoulder being weird. Didn't want to move that way. Didn't hurt it. Little sharp pain. Okay, so the kinetic energy it gets down here is equal to the work it did in lifting it. Okay, because the forces exerted by gravity as it falls are exactly the same as the forces exerted by gravity when it went up. Gravity doesn't care which way you're going. Now, if I'm pushing something up an incline, there's some friction. So if I push it up the incline and then release it and it comes back to its original position, friction acts opposing motion. Friction acts this way when I'm pushing it up the incline. When it's coming down the incline, friction acts that way. So friction goes this way, and that's not path independent. The friction sucks energy out of the system intuitively, but you want to get the whole idea of path independence. So that's what this is. Review the notes from last time, read the book, do something, get that in your head. Net force is conservative force plus non-conservative force. That's not strictly true because a lot of forces are kind of a combination, but it's as if we can split them. So that work is the work done by conservative forces plus the work done by non-conservative forces. Okay. The work done by conservative forces is by definition equal and opposite to the change in potential energy. That's what potential energy is. Talked about it last time. I raised that block. I'm not going to raise it as high because who knows what that shoulder is going to think. Okay, but I raise that block. Okay. Does my potential energy increase or decrease? Do I have more ability for this thing to do work because it's here than here? Yeah, if I release it from here, work is going to get done by the conservative force of gravity. Okay. Now, when I lifted it, was gravity doing positive work or negative work? Well, it was going up and gravity was pushing down. Equal and opposite directions. Gravity did negative work and it does positive work when it falls, which is obvious. Less obvious that it does negative work when it goes up, but if you understand that it does positive work when it falls, it's a short step to the idea that it does negative work when I rise. But that comes back to the definition of work, which is F dot delta S, which I'll talk about a little bit in just a minute. Okay, that's non-conservative. Okay, so your network breaks into potential energy change and work done by forces that aren't path independent. Okay. Again, you can go with your book's terminology and that is kind of equivalent, but I actually like the terminology even better than the terminology that they and I have been using for the last 100 years, and I don't remember what the new one is. Okay. Should have looked, but I was looking at something else. I was looking at the problem sets. And it didn't come up there. Okay. That's what you got to keep front and center. This and this. This is just a version of this because we've just split the work network up here. And of course, this equals the change in kinetic energy. So the change in the kinetic energy plus the change in kinetic energy equals the work done by the non-conservative force. Okay. And that's important. You want to store that away. You really want to think about that. So we have the sum of changes in potential kinetic energy is the work done by non-conservative forces. Okay. Which means that if all your forces are conservative, I toss this chalk to somebody, it won't do that. I want anybody to get hurt. It'd be me, shoulder. Weird. Let's toss this chalk to somebody. There's some air resistance. That's a non-conservative force. Okay. But ignoring that, if you catch it at the same height from which I tossed it, it'll have the same speed because it has the same kinetic energy. Because there's no change in potential energy if there's no change in altitude. It's due to gravity. Now, if you're in a magnetic field, well, you got to think about it in terms of the magnetic field or whatever. Or if it's on a spring, then you got to work this out, okay? On a spring, the sum of kinetic and potential energies ought to always be the same, ideally. Doesn't work out in real life, ideally. Okay. You really got to ponder that. You got to think about that in dozens of problems until you develop the ability to really understand it and apply it. Okay, so just telling you. Something I haven't talked too much about is work equals a dot product of force with distance. The picture of that is here's your force. Here's your delta S. Here's the component of force parallel to delta F. And you should know way more than enough to understand that the dot product is equal to the magnitude of the parallel force times the magnitude of the displacement. So there's only the parallel component of the force that does any work. Okay. If I want to push a car that way, and instead I push it this way, I'm not going to change its kinetic energy. If it's moving along and I just go, okay, I'm pushing it, it's not speeding up, what's wrong? Okay. Well, what's wrong is I'm not pushing in the right direction. I'm pushing perpendicular to its motion. If I want to push it, if I want to speed it up, I get behind it and go with the speed. If I want to slow it down, I get in front of it. Hopefully it's not going too fast. Okay, and push it and do negative work on it, and it'll lose kinetic energy, right? Now, if I trip, it'll run over me, so I don't like to get in front. Yeah, it's going slow enough. I don't know, I have to be going pretty slow at my age. Okay. Okay, does that make sense? That's this, and this are your foundation. Everything else is details. Okay, and the idea that you integrate force with respect to displacement, which probably isn't up here anymore, but it was earlier. Okay. Oh, there it is. Okay. Okay, well, those are your principles. Do a lot of problems and work it out. Wanting you to stop.